This is the third video class in view of the chapter Convection Diffusion for the online course Computational Fluid Dynamics. Myself, Pramod Kothmire, I will be continuing with my third class, and we will be deriving the thermal and momentum Peclet number. So in the second class of convection diffusion, I have given you the idea on advection strength and the diffusion strength. We will continue with that advection strength and diffusion strength, and we will try to derive what is thermal Peclet number and momentum Peclet number. So I will come. So we have F as advection strength, which is rho u, okay, which is also called as mass flux, okay, and we have D, diffusion strength, which is gamma by del x. Okay, now this gamma will keep on changing. For conservation of mass it will be different, for conservation of momentum it will be different, for conservation of energy it will be different. Okay, so let us consider now heat transfer problem. Now let us consider heat transfer problem. In heat transfer problem, okay, we have the change in internal energy, which is m dot Cp delta T, okay, change in internal energy. I'm talking about the gradient, so d by dx, okay, will be always equal to heat conducted. Okay, so Fourier law Ka delta T. Okay, so since I'm talking about the meshing and the gradient, okay, I will put it both the side d by dx. Okay, now this m dot Cp delta T is the change in internal energy, and this is the Fourier heat conducted Ka delta T. Okay, now this mass flow rate m dot can be further written as m dot as rho ua Cp delta T. Okay, rho ua is mass flow rate, which I have told you in the previous class by using continuity equation, and this term as it is Ka delta T. So this delta T, ideally we should cancel it, but since we are learning thermal aspect, we will not cancel it, we will consider it. Instead that area is constant, we will cancel area. So the main important take home is dou by dou x rho u Cp delta T is equal to dou by dou x K delta T. Okay, so K delta T dou by dou x K delta T, Ka delta T by, sorry, one more term is there, delta x delta T by delta x delta T by delta x. So this is simply a Fourier law of heat conduction. Okay, so the take home what I have wrote here is this particular term rho u Cp delta T and this term K delta T by delta x. So we will focus on this term. So I will write this term here, rho u Cp delta T. If you will see this term, I already told rho u is nothing but mass flux, mass flow rate upon area, into Cp delta T. In thermodynamics you have studied one important term called as specific enthalpy. Okay, Cp delta T will always give rise to specific enthalpy. So this is mass flux into specific enthalpy. We call this particular term as advection flux. We call this particular term as advection flux. Okay, on the right hand side you have this as the term K delta T by delta x. Okay, now this K delta T delta x is nothing but the characteristic length K delta T by delta L. Characteristic length I will represent it by capital L. This term we call it as diffusion flux. So here conduction is there, so it is diffusion flux. So in heat transfer problem, there is a balance between the advection flux and the diffusion flux. Advection flux and the diffusion flux. Okay. Now, if you will take, okay, K delta T by delta X, K delta T by L, diffusion flux, and here is the advection. If you will take F as rho U and D as tau delta X, okay, into what? Tau by del X, okay. Now here this tau is nothing but K by C because we are solving energy equation. So this gamma will nothing but K by C dx rho. Okay. If you will take the ratio of this, you will get rho U C, I will write Cp as C delta T upon K by L delta T. Okay, rho u c delta t upon k by l delta t. Okay, we will make one small rearrangement over here. We will cancel this delta t, okay, and we will multiply numerator and denominator by mu, viscosity, dynamic viscosity. So one small rearrangement I have done. I have taken the ratio of advection flux by diffusion flux, advection flux by diffusion flux into, I have multiplied numerator and denominator by dynamic viscosity and I have cancelled delta T. So if I will do the rearrangement, rho u L, this term characteristic length I will take in the numerator upon this mu dynamic viscosity into one more mu is there in numerator, mu, this C left out, mu C and this K, mu C by K. Okay, so this is nothing but advection flux or advection strength upon diffusion flux or diffusion strength. Okay, so if you will see, rho u L by mu is nothing but Reynolds number and mu C by K is nothing but Prandtl. So the ratio of advection strength by diffusion strength is equal to Reynolds number into Prandtl number, and we call this as Peclet number. It is a thermal Peclet number. Okay, so F by D is a multiplication of or a product of Reynolds number and Prandtl number, which is nothing but a thermal Peclet number when we consider this mu as K by C. When we consider this mu as K by C, gamma as K by C. Okay, so this is a thermal aspect. Now let us consider the momentum equation. Now let us consider momentum transfer. So in momentum transfer, diffusion strength is nothing but mu. Okay, so we always write gamma by dx. So this gamma is mu for diffusion strength, and F we have rho u. So when we take a ratio F by D, F by D is rho u by mu by dx. What we get? Rho u dx by mu, which is nothing but Reynolds. So F by D is Reynolds number, which is equal to Peclet number, but it is which Peclet number? Momentum Peclet number. Okay. So in Peclet number we have two things. One is thermal Peclet number, okay, which is a ratio of advection strength by diffusion strength. It is a product of Reynolds number and Prandtl number. It is a thermal Peclet number. And another one is a ratio of advection strength by diffusion strength, which is equal to Reynolds number, which is equal to momentum Peclet. Thank you.